Okay, so we're continuing with the June 2017 M2 paper from Pearson's Edexcel. Yeah, there's always a statics question somewhere. This one is fairly typical, I suppose. I suppose one thing to bear in mind is we've got an unknown angle here, and the first bit is to find the value of R. First of all, I'm going to draw some forces on here. Of course, we're told it's in limited equilibrium, so that's quite important, because that means that we can say the frictional component of the force at B is equal to mu R, and there will be a vertical component which we'll call R. And of course, the other force that we need to put in is the weight. Now, we're told it's a uniform rod, so the weight's going to be 4 meters, and we're told it's 8 meters, so the weight will be 4 meters from B and 4 meters from A. So that's all the forces on here. A good diagram's always a good place to start. Now it's asked for the reaction force, or the component of this force here. It's always worth thinking about where a good place to take moments is. A lot of students have, just by habit, taken moments about B here. There's two problems here. One, you're not going to have R in the equation. Of course, you might get R by adding another equation to it. But also, we don't know beta and we don't know T, so it introduces a lot more unknowns. So just a quick bit of thought into where moments you take about will make life a lot easier. I think sometimes some students are not inclined to take moments about a point where there's no contact, where it's freely, but you can take moments about any appropriate point, and here it's definitely appropriate about C, because T is not going to be an equation, which also gets rid of the problem of beta. So let's take moments about A. Right, now we need, the way I normally look at this is just to think of this component here. Notice that angle there is alpha, and we know that tan alpha is 3/4, so there's no issue there. So this component here is 5G cos alpha, because it's next to the marked angle here. And then we've also got a component of this frictional force. Now notice we've got the alpha here, so that's 2/3 R sine alpha. And we've also got a component of the force that we're after, this R force here, which is perpendicular. And that's, well, this angle here will be alpha here, because that's 90 minus alpha, which makes that angle alpha. So that's R cos alpha. Okay, so that's going to help us get all our moments forces going. So we're taking moments about C. Now let's look at the distances. This is clearly 3 meters from here to here, but it's another 4 from here to here. Okay, so that should make it fairly straightforward. Now the ones that are going in this case clockwise are the frictional force, the 2/3 R sine alpha, and the weight. So let's deal with that first of all. 5G cos alpha is the component of that times by 3 plus 2/3 R sine alpha times by 7, because the distance is 7 along there, is equal to, and then we've just got the one going anti-clockwise here, which is R cos alpha times 7. Right, okay, so I'm going to spend a bit of time just working through this now, but that's actually going to get R in one equation. So nice easy 6 marks if you pick the appropriate equation out. I suspect, I haven't looked at the marks to give me detail, but I suspect that this correct moments equation might be 3 marks in one go. Anyway, so yeah, we can just, well, what should we do? So we divide by cos alpha to get 3/4 and sub in any values we do, but we should have no problems from here. So that's 15G plus 2/3 R tan alpha. Well, let's deal with the 7 as well. So we've got 14/3, because we're times by the 7 times tan alpha, is equal to 7R. Okay, so then we can bring the r's together. So we got, let's take it over to this side. So we got r times 7 minus 14 over 3 tan alpha, and tan alpha is 3 over 4, is equal to 15g. Now this here will be equal to 7 over 2, so that's 7 take away 7 over 2, so that's 7 over 2r is equal to 15g. So r is equal to 30g over 7, which actually works out to be, I think that's exact, probably get the answer, but let's work it out. It actually works out as 42 newtons. Okay, so that's the first part. Now the second part, part B, my natural inclination is in the for when moving further and we need to introduce more equations, is to resolve vertically and resolve horizontally for two other equations. You could take another moment's equation perhaps from here, but then we've still got an issue of an unknown t and an unknown beta. So I'm inclined to resolve vertically and horizontally, but I would. The kind of issue we've got here is that we're not given the angle. The angle we're being asked for, beta, is not the horizontal angle. So I'm going to work that angle out first, because it will make our resolving equations easier. So if I call that angle theta, then the resolving equations are going to be easier, and because I know r, everything's going to be in terms of r. I should be able to kind of work my way through to an answer. So I'm going to work out everything in terms of t and theta and r. So resolving vertically and resolving horizontally. Let's resolve vertically first. Obviously we've got the r force going upwards. We've also got the component of the t force going upwards here. That will be t sine theta. And that will be those two are going upwards, and that will be equal to 5g. But remember, r is equal to 30g over 7. So we have t sine theta is or we could just say 5 times 5g take away 42. 5g, so that's equal to 7 newtons. 5 times 9.8 is 49, so 7 newtons is the horizontal force, the vertical t component of t sine theta. Now if we do the horizontal, right, now we've only got two forces at play, because r is not in it, neither is the weight, but we've got we've got this force here, so that's 2/3 of r, and we've got the horizontal component of the weight, because it's next to this angle theta I've marked. That's going to be equal to t cos theta. But t cos theta is equal to 2/3 times 42, and that equals to 1428 newtons. So if we divide these two, we'll get t sine theta over t cos theta, which is of course equal to tan theta. Make sure we get them the right way around. That's 7 over 28, which is equal to 1/4. So we can work out theta, but remember, we've done the hard work. Remember that the actual angle here is beta that we want. So beta, which is equal to theta plus alpha, because this angle here is alpha, clearly, which is equal to arctan 1/4, which we just worked out, plus arctan 3/4, because that's the angle we're given, alpha, and that I believe comes to, I've worked out before, 50.9 degrees. Okay, so moving on to question 6. It's projectiles question. A few people were put off by the fact that there's two projectiles, but shouldn't have caused too many problems really. We've got two unknowns here, and we set up kind of simultaneous equation part A to get our answer. Well, the thing is, it's told that these two things collide after 2 seconds. So you've got one going this way one going this way, say, so that looks like a complete projectile because we've got one going that way, the other one going the other way, and they collide after 2 seconds. So it's not one single projectile there. It's probably not the best of diagrams, but anyway, so we know that the horizontal distance is equal to 40. Well, that means that because this one will have moved by some the distance here will be 30 cos 60 times 2, and this one will have moved by q cos theta times 2, and the total of those is 40. So we've got 30, and it's because the speed horizontally, of course, is constant. Okay. So, and that's fairly clear. So I've got 30 cos 60 times 2 is equal to q cos, oh no, it's not equal to, the two add up to 40. Okay, so rearranging that, cos 60 is equal to half, so that gives me 2q cos theta equals to 10, so q cos theta equals to 5. So that's the first bit of information that's going to prove useful to us, and then we can use the fact that the vertical distance is the same. They travelled the same height, vertical height, the same when t equals 2. Okay, so we're going to apply, in this case, the things that we know, of course, are our u. Now, of course, our components now vertically here is 30 sine 60 is the vertical component of the height here, and this one's q sine theta. We also know t. So we're basically going to be using s equals to ut plus a half at squared on both of them, and using the fact that they're the same. So we've got for p 30 sine 60 times 2. G is obviously minus 9.8 plus a half times minus 9.8 times 2t squared. So that's for q. It's going to be the same for p. It's going to be the same height as for q. So that's q cos q sine theta times 2 plus a half, I said t squared there, but it's 2 squared of course, plus a half times minus 9.8 times 2 squared. Now actually those bits cancel. It's quite interesting what happens there. So that gives us the 2 cancels here, so that when we work that out, that gives us q sine theta is equal to 15 the square root of 3. So there's our simultaneous equation. We might as well work them out in the order we're being asked for. So a bit similar to the last question, we divide the 2 to get tan theta. So tan theta is equal to sine theta over cos theta, so that's 15 over square root of 15 square root of 3 over 5. So that equals to 3 the square root of 3. The inverse tan of that, so theta equals the inverse tan of that, which is 73.9. 3 square root of 3 is equal to 73.9 degrees. My apologies, must have had the wrong number written down now. It's actually 79.1 degrees, of course. Okay. Now, for the second part, for part B, oh no, we're on part B, we're on the second part of this first. Well, you might use the angle you've worked out and put it in there, but a slicker way is to square this. That's q squared cos squared theta, and square this and add them together. So q squared cos squared theta is equal to 5 squared, and add that to the square of q squared sine squared theta, and that equals to 15 times by 3 squared equals to 675. 25. So that gives us q squared times cos squared theta plus sine squared theta equals 700. So q squared equals 700. Taking the square root of that, we'll get q is equal to 26.5 degrees. There we go again. It's not degrees, of course, it's not an angle. Meters per second. You don't get penalised for lack of units, so I think the examiner, if you wrote that, would just shrug their shoulders and think, what the hell are you doing? But you wouldn't be penalised for it. Anyway, let's do it, right? Meters per second. Right, okay, so then part B. So part B talks about the speed at which it collides. In other words, the speed after t equals 2, because we know that it's 2, and it's talking about the velocity of p, not q, probably because they know that you know p, so it's going to be easier to mark. So we've still got the horizontal component after 2 seconds. We've still got the horizontal component. It's still going to be what it was always, because that's constant. So that's 30 cos 60, which is obviously equal to 15. We'll call that Vx, I suppose. Now Vy, we can use, that's going to be affected by gravity, so we can apply V is equal to U plus AT vertically. So we'll call it, but remember it's the vertical velocity component of the velocity you've got here. Vy is equal to the initial. Now initially we've got this as 30 cos 60 going 30 sine 60, so to say, upwards. So that's 30 sine 60. Now acceleration is minus 9.8, or deceleration, times by 2. Right, now that comes to approximately 6.38, although I've got the number stored there. It's actually 6.3807 blah blah blah, but we're okay, so we can now just work out the speed. It's using Pythagoras on that. So the speed is these two components squared, added, and then square rooted, which is basically Pythagoras. So that's 15 squared plus 6.38 using the exact number squared, and that comes to, when we work it out, 16.3 meters per second. Okay, so one more question to go and then we're done with this paper. Okay, so here we go. Okay, question 7. It's a collisions question. First part's about impulse. Well, it's pretty straightforward really. We've got two particles, but for the first part it's talked about particle B being projected towards the wall at speed 5u. And because the coefficient of restitution is 3 over 5u, and 3 over 5 times 5u is obviously equal to 3u, so it's coming back with speed 3u, And then it's just to find the impulse. So the impulse is equal to change in momentum. Magnitude of impulse is equal to change in momentum. So we just basically add these two together because they've changed direction anyway. And we only want the magnitude of it. So we've got the mass, which is, make sure we've got the right mass, that's 4m for B. And these two added together because they're going in the opposite direction. So that's 32 mu. So I'm bothered to put units on, it hasn't asked for them. But we could. So yeah, we can move on to the next part, which is the more meaty part. Now part B, it's a standard thing now. For part B, what's happening is, we've got, obviously this is now B going in this direction. This is our before situation. And then afterwards, we've got these two going along with their velocities. Let's call this one V and this one W. I don't always use these symbols, but looking ahead, this isn't multiple collisions, so we're not going to run out of symbols. Sometimes I use a numbering system, V1, V2, V3, and so on. But here we've only got those two, so I'm going to use V and W. Right, so this is going with speed 3u, so we're going to set up our equations. Conservation of linear momentum. Obviously everything here we're going to consider positive. So we have, making sure we get the masses right, that's 4m, that's 4m, this is 3m. So we have 3m times w plus 4m times by v is equal to 4m times 3u. Obviously the m cancels, leaving me with 3w plus 4v is equal to 12u. Okay, and then I'm going to use Newton's law of restitution. Now, it's not the same E now, of course. It's a different E because it's between the two particles. So that's speed of separation over speed of approach. Now, they separate each other. This one's the quicker one, the W, take away V. Taking care that the signs are positive, I always think. W take away V, and this is approach, there's only one there, is equal 3u, is equal to E. So W take away V is equal to 3UE. Now we're being asked to show that are both moving in the same direction. So bear in mind that everything is positive in it. We're taking everything positive in this direction. W, of course, is going to have to be positive because it was originally velocity 0 anyway. So it's going to have to be moving in this direction. So it won't be necessary to work out W. But V could reverse direction. If it were reversed, our sign would be negative. But if it's not reversed, which is what they're telling us happens because they're going in the same direction, V would be positive. So I'm going to get an expression for V and then show it's positive. So we need to eliminate W. So I'm going to times this one by 3. So we've got 3W take away 3V is equal to 9UE. So then I'm going to subtract, okay, this expression from this expression, the other way around. Basically we're going to subtract these two. So 3w take away 3w 0, 4v take away negative 3v is 7v, is equal to 12u minus 9ue. So tidying that up a bit, v is equal to, I might as well take 3 out as a factor, 3 and u out as a factor over 7, and then that's 4 take away 3e. Now the thing is, because e is going to be greater than or equal to 1 and we're subtracting 3 here, e here, that means that v must be greater than or equal to 3u over 7, 4 take away 3, which of course is equal, which is 3u over 7 basically, so 3u over 7, which is greater than 0. So that means that sign does not change, so they move in the same direction. Okay, so let's look at the last part of this question again. It says the kinetic energy of B. Okay, so we're still on this particle here, is 1/4 of the kinetic energy immediately before its collision with A. So it's got a quarter of its kinetic energy afterwards, and we've got an expression for it here, its velocity. So Ke for B, let's label it because it's part C. For B, the Ke before is equal to Ke after, because it's a quarter, times by 4. Okay, that's the right way around, isn't it? Yeah, because this is a smaller amount, it's lost that amount of energy, so times that by 4 you'll get the Ke before. Now Ke before, we're told it's 3u, so that's half times by 4m times by 3u squared is equal to a half times 4m times by this squared, so that's 3u over 7 times 4 minus 3e squared, and that's times by 4. Obviously all of this stuff is going to cancel here, so just taking a bit of care now really, I would say. We've got 9u squared here, and here we've got 9u squared over 49, 4 minus 3e squared times 4. So we want to get the value of e from this, which we can do. Obviously the 9u squares now cancels. Now I'm sure many of you might be tempted to multiply out the brackets here. I suppose it's okay, but I'm not going to. A little bit more efficient, I think, to take square roots from there. We've got 49 over 4. Yeah, so take square roots on both sides. Now I'm not sure whether the positive or negative one aspect of this square rooted is going to be required, so I'm going to write it as this to be careful at the moment. Rearranging that, I get 3e is equal to 4 minus or plus 7 over 2. Obviously the positive one now will not yield anything because our e is going to be too big. It'll be greater than 1. So e is equal to 4 minus 7 over 2 divided by 3. So that's 4 minus 7 over 2 is equal to a half divided by 3, so that gives e equals to 1 over 6. Okay, so that's that paper done. We're all done with June 2017 now. And there's just one more paper in this whole series, which is next year. So this might be the last, well, it will be the last M2 paper that we do, although we might do some international ones yet. Okay, thanks, bye.